Hello everyone, my name is Joshua Pulsifer and I'll be talking to you today about tackling infinite dimensional problems using InfiniteOpt and the abstraction that goes behind it to make this all possible. And what I hope you can take away from this is that as we view problems in this way, it'll help us to promote innovation in these spaces, and that InfiniteOpt provides a very powerful and useful interface that is useful to a very wide audience. And this is an overview of what we'll be covering today. And with that, let's jump right into it. So first we have infinite dimensional problems, which are problems that involve an infinite set of decisions that need to be made. And this encompasses a wide range of problems and fields we might encounter, such as stochastic and dynamic optimization, which each employ diverse theories and techniques that are very useful. And what we want to do is develop a unifying abstraction to commonly express all of these, bridge the gaps between them such that we can apply this theory across the board to the other fields such that we can innovate. And the challenges that come from doing this, of course, would pertain to trying to generalize out of very specific things, such as, for example, what does a chance constraint look like in the time domain? And developing a platform that's very easy to use, but also robust enough to be used in cutting-edge research. So then this leads us to the abstraction that makes this all possible. And to motivate it, let's consider two common problem classes, such as that of space-time optimization and stochastic optimization. Well, they all involve and employ infinite parameters, such as time and uncertain variables that depend on a particular statistical distribution. Then infinite variables, which are functions of those infinite parameters. They could have finite variables, such as an infinite variable defined at a particular point, or perhaps design or first stage variables. They can have derivatives that operate on the infinite variables. They could involve what are called measures, which could be, for example, integrals, or expectations or risk measures. And then there incorporate constraints, which can comprise anything mentioned above in accordance with what's needed to model the given optimization problem at hand. So then with all that in mind, we can begin by discussing infinite domains, which are domains that comprise infinite cardinality. So we could think of, for example, a continuous interval going from 0 to 10, and this could be either univariate, or perhaps even a multivariate domain. We could then define infinite parameters, which are going to live on these infinite domains. So we could think of, for example, time. And with all of this, we can define what would be called the problem domain, which is just going to be the product of all the infinite domains involved in a particular problem. And this is all in juxtaposition then to traditional optimization models that typically consider finite domains, where we define some variable over some finite cardinal set. So we'd have like 4 variables y at a particular index for each one. So then we can think about decision variables. And first we have infinite variables, which are measurable functions that intake as input give a particular infinite domain and map it to the domain of the variable. So we could think of, for example, a variable y depending on time, spatial position, and uncertainty. We could then define semi-infinite variables, which are also measurable functions where a portion of the infinite domain has been evaluated or collapsed. So as exemplified here with this y being defined at time 0. We could have point variables where a particular point in the domain is used to evaluate the variable, making it finite. And then we could think of just regular finite variables such as design or first stage variables that we commonly encounter in traditional optimization problems. With this, then we can consider derivatives, which themselves are measurable functions that take in as input infinite variables or expressions and inherit the infinite domains associated with those arguments, making derivatives infinite variables. And we could think of, for example, a second partial derivative. We could think of the Laplace operator. We could think of taking the derivative with respect to an uncertain parameter of an integral. We could start to come up with all kinds of different things we might wish to employ. From there, we can start to think about measures, where a measure is an operator that operates on a particular variable or expression. and it's going to operate over a particular infinite domain and evaluate over that domain, removing that dependency. So we could think of, for example, an integral over the time domain, or like a probability over a particular random space. We can then consider constraints, which will be comprised of anything we've mentioned so far, including measures and derivatives, and whose infinite domain will be comprised of whatever constituents they contain. It could be even defined over some subdomain of that infinite domain. You can think of, for example, a point constraint. And these can encapsulate a wide variety of things needed to model our problems, such as chance constraints or algebraic differential constraints, etc. So with this all in mind, then we come to our package, InfiniteOpt. This is a Julia-based package based off of JUMP that can be used to tackle infinite dimensional optimization problems. And what makes this different from a lot of the other packages and software that exist out there? Well, principally, this employs the abstraction I've just been explaining, including measure operators and derivative operators. It also directly integrates and facilitates modeling for random spaces, and it's based in Julia. Moreover, it employs a wealth of capabilities, including a very intuitive symbolic interface. It directly models and handles infinite domains, measured operators, derivative operators, event constraints such as chance constraints. It features efficient automatic transcription capabilities. It's highly extendable, and we provide extensive documentation to help you along the way. So let's look at what this looks like. So first, we can think of infinite domains. We natively support continuous intervals and statistical distributions, the codomains, rather, of those distributions. So we could consider, for example, defining a time parameter over a particular interval, or a parameter S over a semi-infinite domain, or a spatial parameter X over a domain of our choice, even perhaps specifying a particular grid system or supports that we want to use, and an uncertain parameter with respect to a statistical distribution of our choice. We then can define decision variables. So for example, a three-dimensional infinite variable here, or this semi-integer infinite variable, and point variables, which is, for example, w at a particular point in time and space, and finite variables, which we call hold variables, following a very JUMP-like syntax. We also can define derivatives of any particular order over just about any kind of expression, applying the necessary calculus behind the scenes to make it all work. So for example, we could take here the second partial derivative with respect to time. We also provide this nice Unicode functional interface to make it more compact and symbolic to express things like this more complex derivative here. Or we could think of something a little more exciting, like taking the derivative with respect to an integral. And then we can think of measures. So we support, for example, integrals and expectations, and even risk measures or measures that are defined by the user following an API we provide to allow custom measures that we wish to use modeling our problem. So then putting this all together, we would model a problem by defining an infinite model, adding in our parameters following our symbolic compact interface, adding in our decision variables in a JUMP-like manner with their associated properties, compactly defining complex objectives such as this one of both an expectation and integral, add in constraints of our liking such as these chance constraints or differential constraints, and again, a very compact and easy manner, and then solve it by simply pushing optimize and gathering our results, and all this but 15 lines of code. So now once we have a model defined, the question is how do we go about solving it? So we define our infinite model, we'll apply some sort of reformulation method that we wish to employ to convert it then into a finite JUMP model that we can actually solve. And we provide the framework necessary to provide a seamless experience for the user between the two. By default, to go about solving this, we provide automatic transcription or discretization with the necessary techniques such as trapezoid rule or Monte Carlo sampling for the measures, and techniques for derivatives such as orthogonal collocation over finite elements. And we employ a very sophisticated support or grid management system behind the scenes to make this all possible. Moreover, I want to highlight this is very performant. Here we can compare it to just doing manual transcription with jump, and we can see that we scale to order n, and that we have minor overhead compared to manually transcribing a problem with just jump. And we don't have to worry about trying to implement any of these more advanced evaluation techniques ourselves and avoid a lot of the bugs that would come from doing so. Moreover, as I mentioned at the beginning of my talk, we want to innovate across these different infinite spaces. And one way that InfiniteOpt is very useful in helping us do that is as we come up with novel techniques, as solution techniques or modeling paradigms that we want to employ in these spaces, InfiniteOpt is very convenient because just about any aspect of it is extensible. And we provide detailed documentation to guide you step by step to go through implementing your own techniques such that you can test bed them very quickly with InfiniteOpt. So with that, let's get a feel for what InfiniteOpt looks like with the case study. So what we're considering here is pandemic optimal control, where what we want to do is we have a particular contagion, and we want to optimize the social isolation or distancing policy that we want to enforce, but also minimize any unnecessary economic impact that we can avoid. We're going to model this using what's called the SEER model, which considers 4 populations, those of being susceptible, exposed, infectious, and recovered, and then uses this variable U that enforces a sort of mandatory quarantining policy to isolate infected individuals. Here, because this might be some sort of new disease, we'll consider the incubation constant XC to be uncertain. We don't know quite what it is, but we know the distribution that it might follow. And what we want to do is control the amount of infected individuals relative to a particular tolerance. And to model this, then, we can consider this optimization problem, where we're trying to minimize the social distancing policy U over our time horizon relative to our contagion model. Here we have this time expectation, where what it does is we're trying to limit the amount of infected individuals relative to our threshold, perhaps putting it to a certain time tolerance, epsilon, over time, and then we define these final parameters to motivate our uncertainty and the control parameter U. So now if we model this in InfiniteOpt, we would define our constants, initialize our model, add in our infinite parameters, along with the support grid we want to use, and the derivative technique, in this case, orthogonal collocation, define our decision variables. We could then add in our objective and our constraints very compactly, optimize, and then we can obtain our optimum policy. And what we can see here is as we modulate the mandatory distancing, that we're able to effectively control the disease within the desired parameters while simultaneously considering the uncertainty we have and some of the disease characteristics. So bringing this all together, I would encourage everyone listening today to check out our GitHub page. This is a registered Julia package, and we have extensive documentation to guide you through step-by-step on how to use it. And we would love to hear back from you about your experience, the things that went well for you, or perhaps features or things you'd like to see improved. And I'd also like to acknowledge the support I've received from the University of Wisconsin and the Department of Energy, and I'd be happy to discuss this further with any of you and answer any questions that you may have. Thank you.